Hi, welcome to Chemical Reactions Review Part 1. My name is Dr. English, and in this review we're going to look at the basics of chemical reactions. Specifically, we're going to talk about what is a chemical reaction. We're going to look at physical versus chemical properties. We're going to decode the chemical equation, really break it down and see what's involved. We're going to talk a little bit briefly about the law of conservation of mass. And finally, at the very end, we're going to go over the basics of how to balance a chemical reaction. So the first question is, what is a chemical reaction? And the definition that we're going to look at is that a chemical reaction is a process by which one or more substances are converted into new substances with different physical and chemical properties. So in this example right down here, I have this reaction represented technically three different ways. So I have elemental magnesium, so solid magnesium metal, reacting with atmospheric oxygen to produce magnesium oxide. And this would be a combustion reaction. We would have to burn magnesium in oxygen to produce magnesium oxide. Symbolically, the way that we would represent this is the magnesium symbol, a plus sign, diatomic oxygen yields, and then the chemical formula for magnesium oxide. We're going to talk about this step by step and how we would approach this. Let's talk a little bit about physical versus chemical properties. A physical property is a quality or conditions of a substance that can be observed or measured without changing the substance composition. So some examples of physical properties might be like boiling point. We can check the boiling point of a substance without technically changing the overall chemical composition of a substance. Color, density, hardness, mass, and volume. Both mass and volume can be measured. So these are all examples of physical properties. Then we have chemical properties. And a chemical property is going to describe how an element behaves during a chemical reaction. So what exactly is going to go on? Some examples of chemical properties might be chemical stability, flammability, reactivity, or toxicity. The list of physical and chemical properties definitely goes beyond what I have listed here as examples. So this would be for a chemical property, how it's behaving during a chemical reaction might be like, can something burn? Or is it going to bubble or fizz? Or how reactive is it going to be? Is it going to be slightly reactive or very reactive? And how are we going to see those reactive tendencies occur? What are we going to observe? So these are just some general characteristics of physical versus chemical properties. Now let's talk about decoding the chemical equation, breaking it down and looking at the parts that you need to include when you write out one of these reactions. So a chemical equation is going to symbolically describe the reactants and the products of a given chemical reaction. So the first is, what is a reactant? Well, a reactant is the substance that enters into a chemical reaction, what you are starting with. Then we have the product. And the product is defined as a substance that is produced by a chemical reaction. So what are you ending up with? The symbols that we associate with reactions is the plus sign for one, and that means reacts with, plus, combines with. There's a whole bunch of different ways that you can represent in a word equation the plus sign. And then we have the arrow, and the arrow can mean yields, gives off, produces, all sorts of different descriptions that's going to say this is what you're going to produce as a result of this chemical reaction. What we don't see in a chemical reaction is a negative sign. So no negative signs. No negative signs. And that's a common issue that sometimes students have, is they want to put in a negative sign to represent the loss of something. And to that, my friends, I say no. No negative signs. Do not include them. So the only thing that we're going to see in a chemical equation is a plus sign and an arrow. So let's look at two chemical reactions and how we would approach writing them. So let's read through the reaction first and then slowly start to break it down. So an aqueous silver 1 nitrate solution reacts with solid copper to form a solution of copper 2 nitrate and silver metal. So if I was approaching this problem, the first thing that I would do is just start writing out my symbols and ions if necessary. The first thing I see is silver 1 nitrate. I know the symbol for silver is Ag, and this Roman numeral right here is telling me that it is plus 1. And then I go to table E and I look up nitrate, and that is NO3 minus 1. Reacts with, that's going to be a plus sign, solid copper, which just means copper metal, so I'm just going to represent that with a Cu, to form, that'll be my arrow, and then a solution of copper 2 nitrate. So the symbol for copper is Cu, the Roman numeral tells me it's plus 2, and then the nitrate, NO3 minus 1, the and is going to represent a plus sign, and silver metal, and I know that the symbol for solid silver or silver by itself is just Ag. Now that I have all this information, I'm actually going to put it together in a chemical equation. I'm going to recopy Ag plus 1 and NO3 minus 1 because I want to take the time to make sure that I write these correctly. So Ag plus 1, NO3 minus 1, I know that the plus 1 and the minus 1s are going to cancel each other out. So that's going to be AgNO3 for my formula. Plus, there's my plus right there, and then solid copper, so it's just going to be Cu, my arrow, and then I'm back to looking at my next formula. So my next formula is Cu plus 2, NO3 minus 1, and I'm going to cross these down. That's going to be absolutely key here. So the plus 2 is going to go down here, and the minus 1 is going to go down here. But I remember back to my chemical formulas review, and what's the mantra? No positives, no negatives, no ones. But I do need to put parentheses around the NO3 because it would look really strange with it as NO32. That's a little bizarre. So if I recopied it, it would be Cu, parentheses, NO3, end parentheses, and then a subscripted 2. And then we have our plus sign again, and then finally our silver metal. So that's very slowly, very carefully translating our equation to represent it symbolically. Let's look at our next one. When heated, calcium carbonate, so Ca plus 2, carbonate, I looked that up on table E, CO3 minus 2, decomposes is going to be represented as an arrow, into calcium, Ca plus 2, oxide, O minus 2, and carbon dioxide, molecular compound, so CO2, subscripted 2. So again, what I'm going to do is I am going to bring everything down, make sure that I write the correct formulas, and pull it all together at the end. So the first one I have is Ca plus 2, CO3 minus 2. So the plus 2 and the minus 2 are going to cancel each other out. So this is just going to be represented as CaCO3. And then decomposes, that's my arrow, into calcium oxide. So that's going to be Ca plus 2, O minus 2. And again, very conveniently, these are going to cancel each other out. So bye-bye, bye-bye. So this will really be CaO plus, and then finally carbon dioxide. I can just translate that right from the words, so CO2. So again, it's important to take your time, check your reference tables, especially your periodic table and table E. Make sure that you have the right charges, make sure that you have the right polyatomics. Really follow carefully the crossing down and writing the formulas, because the next thing that we're going to do is balance it, and it's almost impossible to balance things if the formulas aren't written correctly. So before we get into balancing, let's talk about the law of conservation of matter, or the law of conservation of mass. Really, what is the definition of this law? And it's the basic idea behind this law is that matter is not created nor destroyed. So technically, in a perfect world, whatever we start with, we should end with, or at least be able to account for. So what does that mean? Well, it means the total mass of the reactants needs to equal the total mass of the products. And again, theoretically, we should be able to account for everything. So for mass to remain constant, again, going back to the mass of the reactants equaling the mass of the products, the number of atoms of each element must be the same before and after a chemical reaction. We need to be able to account for everything. So when the law of conservation of mass is obeyed, this is called a balanced equation. And again, Since this is a review, I'm just going to do some general balancing, highlight a couple of important things, and then move on. So let's talk about the steps for balancing a chemical reaction. The first thing is to start with the correct formulas. That's absolutely key. So let's look at this reaction right here. Calcium metal is dropped into a beaker of water. Calcium hydroxide is formed and hydrogen gas is released. Let's see, what am I going to write here? So calcium metal, that's represented as Ca, so metal by itself, is dropped into a beaker of water. I'm going to say that's going to require a plus sign. I know the formula for water, H2O. H2O. Then it says calcium hydroxide is formed, which means I need an arrow because that's indicating that calcium hydroxide is a product, and hydrogen gas is released. So calcium hydroxide. Calcium is Ca plus 2. Hydroxide is on table E. It's polyatomic. So that is OH minus 1. What I'm going to want to do is take this and cross it down to here. Take this, cross it down to here. No negatives, no positives, no ones. I'm going to need parentheses around the OH. So this is going to be Ca parentheses OH end parentheses 2. Don't just assume that the Ca and the OH can be shoved together, because if you do that, it's going to be really painful later on when you realize you can't balance the thing. Take the time, write the ions, confirm that your formulas are correct. So critically important into this whole process. So CaOH2, and that's a plus sign, and then hydrogen gas. Hydrogen is a diatomic, so that is H2. So I look at this, I double check my work, everything is good. The next thing that I'm going to want to do is count the number of atoms of each element. So if I quickly rewrite this, there, I've rewritten it. So now what I'm going to want to do is go through and count how many of each element I have. And sometimes you need to do this, sometimes you don't. It depends on the actual reaction that you're balancing. So if I look at this, Ca, there's one Ca here. There's a subscripted 2 by the hydrogen, so that means there's 2 hydrogen atoms, 1 oxygen, because there's an assumed 1 down here, 1 Ca on the product side. This 2 is going to be distributed. We know that there is an assumed 1 here and an assumed 1 here, so that means there's 2 oxygens and 2 hydrogens, and finally there's 2 hydrogens involved in the diatomic. The next thing, after I have labeled everything, I'm going to look for polyatomic ions. Now, there is a hydroxide here, but the hydroxide is not represented over on the reactant side, so I'm not really going to use that particular shortcut at this time. Balance the elements that appear only once on each side. That's a nice way to start. It doesn't always work, but that's what I typically advise my students to do. Look for the element that appears only once and start with that one. And then finally, we're going to place coefficients in front of the substances as needed until everything is balanced out. If we go back to this one more time, we said that we had 1 Ca, 2 hydrogens, 1 oxygen, 1 calcium, 2 oxygens, 2 hydrogens, and 2 hydrogens. So if I was to start here, I'd start with the calciums. So 1 calcium, 1 calcium. We're in good shape. Then the next thing I would do, and actually I'm going to underline those to say to myself, hey, I've checked that element. The next thing I would do is I'd look at my 2 remaining elements, hydrogen and oxygen. Which one should I go for? Probably the oxygen, and here's my reasoning why. The hydrogen appears only once on the reactant side. Fine. But there's 2 hydrogens on the product side. So I'm going to balance the oxygen first just to see if I can make things work out. So I have 1 oxygen here, 2 oxygens here. So I need to have 2 oxygens over my reactant side. So I'm going to throw a 2 in front, and I'm going to say I'm going to balance my oxygen. So I'm going to put a line underneath just to acknowledge that I'm working on this one. Now this 1 is really a 2, and this is a 2 over here, so we're good. Unfortunately, because we have put the coefficient of 2 in front of the water molecule, I've messed with my hydrogens. So I no longer have 2 hydrogens, I actually have 4, because 2 times 2 gives me 4. So I'm going to write that 4 over the top. So 1 calcium, 2 oxygens, 2 oxygens, 4 hydrogens, and since this is the last element to be balanced, I'm sort of hoping that everything works out. I'm going to go over to my product side and I'm going to say, well, this 2 distributed to this hydrogen, so that means there's 2 hydrogens here, and hey, look, I have 2 hydrogens as part of my diatomic, so 2 plus 2 gives me 4. Yay! So now I could say 1 calcium, 2 oxygens, 2 oxygens, 4 hydrogens total over here, 4 hydrogens total over here. We're balanced. We're good. The last thing that you want to do is just make sure all the coefficients are in the lowest possible ratio. So in other words, right now if I look at this, this is in a 1 to 2 to 1 to 1 ratio. If there was a coefficient of 2 to 4 to 2 to 2, I'd want to reduce that down, divide everything by 2 to get back to my 1 to 2 to 1 to 1 ratio. That's what they mean by lowest possible ratio. Let's do a couple more examples. Let's look at this first one here. Diatomic nitrogen, diatomic hydrogen, and ammonia. First thing that I'm going to do is count the number of elements that I have. So I have 2 nitrogens, 2 hydrogens, 1 nitrogen on my product side, 3 hydrogens over here. Now there's 2 ways that I could approach this. Both of these elements only appear only once, symbolically, on each side of the equation. For this one, it doesn't really matter whether I start with the nitrogen or the hydrogen. I'm going to start with the hydrogens just because there's more of them. So I have 2 hydrogens here, I have 3 hydrogens here. The lowest number that they'll both divide into evenly is 6. I'm going to throw a 3 in front of here and a 2 in front of here to balance out my hydrogens. So 3 times 2 gives me 6, and 2 times 3 gives me 6. So now my hydrogens are balanced. Then I'm going to go to my nitrogens. Well, I have 2 nitrogens here. Originally, without the coefficient, I only had 1 nitrogen, but oh, look at that. Because the 2 is now going to distribute through the whole formula, I now have 2 nitrogens. So nitrogens are balanced, and we're good. Let's look at our next one. We have iron metal plus sulfuric acid gives me iron 2 sulfate and hydrogen gas. Let's go through and again count our elements. 1 Fe, 2 hydrogens, 1 sulfur, 4 oxygens, 2 here. The 3 is going to distribute through, so 3, 12, and 2. But you notice I'm looking at this and I'm thinking to myself, is there a shortcut? And there is, which is great, because what I see here on both sides of the equation is this sulfate polyatomic. The only time that the sulfur and the oxygen appear is part of the polyatomic. Now this is a shortcut. Sometimes you can use this, sometimes you can't, so you have to be careful. So I'm going to say, well, there's a sulfate ion right here, and there's one sulfate ion. And there's 3 sulfate ions over here. So instead of having the 3 and the 12 and the 1 and the 4, I'm going to put 1 and 3. Okay, I want to balance those sulfate ions. I'm just gonna go for it right away. So in order to balance it, I have 1 sulfate ion over here, I have 3 sulfate ions over here, so I'm going to put a 3 in front of this sulfuric acid. So now 3SO4, 3SO4, that's balanced. I'm going to use blue to show that I've balanced that. Now, how does that affect everything else in my equation? I have to look at my hydrogen atoms, I've got to look at my iron atoms and try to balance them out now. Let's look at hydrogen. 3 times 2, that now gives me 6 hydrogens here. So what do I need to do to get 6 hydrogens over here? Well, if you said, hey, Dr. English, you should throw a 3 in front, you'd be right. So 3 times 2 is 6, 6, and 6. The hydrogens are balanced. The last thing that I have to do here now is look at my iron atoms because those are the ones that are left over. I have 2 here, I have 1 here, so I just need to throw a coefficient of 2 in front of here. That's going to change this to 2. This already is 2, and I'm balanced. For me, everything is underlined. I can go back, I can check. Of course, you could actually separate the sulfur and the oxygen and do it that way. Absolutely fine. This is just a little shortcut. The last situation that we have here is a combustion reaction. We're going to take C2H6, we're going to basically burn it in atmospheric oxygen to produce carbon dioxide and water. Propane plus oxygen gives you carbon dioxide and water. For me, there's very specific steps for balancing combustion reactions that really I like to follow in order to keep my sanity. And the first thing that I like to do is start out with the carbons. So I'd look at this and I'd say, well, 2 carbons, 1 carbon, so I'm going to throw a 2 in front of here, and that'll give me 2 carbons. I always start out by balancing my carbons. Then I go to my hydrogens. And again, there's a very specific reason. Hydrogen appears once on the reactant side, once on the product side, while the oxygen atoms appear once on the reactant side, but 2 times over on the product side. So I'm going to stick with what only appears once on each side first. I have 6 hydrogens. 6. I need 6 hydrogens over here, so I'm going to put a 3 in front, and I'm going to make this 6. And then finally, the last thing I'm going to do is balance my oxygens. So now I look at this and I say, well, 2 times 2, that's going to give me 4 oxygens. 3 times, technically 1, that's going to give me 3 oxygens. And oh no, that's going to give me 7. Well, I don't want to use fractions in my equation. Your teacher might say, hey, that's absolutely fine. Use the fraction. Personally, though, I don't use fractions in my equations. So instead, what I would tell my students is pause, erase. I tell them to put a 2 in front of the C2H6. So I'm going to take a moment and erase this, and I'm going to go back and I'm going to start by putting a 2 in front of the carbon. So 2. Again, I'm going to follow the same steps. I'm going to balance the carbons, I'm going to balance the hydrogens, I'm going to leave the oxygens for last. So 2 times 2 gives me 4 carbons. So I'm going to put a 4 in front of here, so 4 carbons over here. Then I'm going to look at my hydrogens. 2 times 6 gives me 12. So I need 12 hydrogens over here. So that means 6 times 2 gives me 12. And then finally, I'm going to look at the oxygens. So 4 times 2, that gives me 8 oxygens. 8. 6 times, again, are 1. So 6 times 1 will give me 6. So I'm going to bring that 6 down here. And 8 plus 6 gives me 14. That's an even number. That's good. I can use 14. So that just means a 7, a coefficient of 7 in front of the O2. And then I'm going to take a moment and I'm just going to double check everything one more time. So 2 times 2 gives me 4 carbons, 4 carbons over here. 2 times 6 gives me 12 hydrogens. 6 times 2, 12 hydrogens over on my product side. And finally, 7 times 2, that gives me 14. 4 times 2 gives me 8, bring that down. 6 times 1 gives me 6, bring that down. 8 plus 6 gives me 14. I'm good to go. I'm balanced. Sometimes you can just balance these combustion reactions without having to do this, but other times you do need to double everything in order to get a whole number in front of the diatomic oxygen. So what did we learn in this review? Well, we went over the basics of chemical reactions. We talked about physical versus chemical properties. We decoded the chemical equation, looked at the parts of it. We talked a little bit about the law of conservation of mass or matter. And finally, we went through how to balance a chemical reaction. Need more help? Feel free to contact me, and I'm always looking for feedback. Have a great day.